One of the most recognizable physical properties of alkali metals is their silvery appearance. When an alkali metal such as lithium, sodium, or potassium is freshly cut, it has a bright, shiny, silver-colored surface with a beautiful metallic luster. This shiny appearance is a common property of most metals and occurs because the free-moving electrons inside the metal reflect light very efficiently. However, unlike many other metals, the shiny surface of alkali metals lasts only for a very short time. Within seconds or minutes after being exposed to air, the bright silver surface gradually loses its shine, becomes dull, and changes to a grayish appearance. This rapid change is one of the characteristic properties of Group 1 elements. The image shows a freshly cut piece of sodium with one half appearing bright and shiny, while the other half has become dull after exposure to air. This comparison clearly demonstrates how quickly alkali metals react with the atmosphere. Immediately after cutting, the fresh surface reflects light strongly because it is clean and smooth. As soon as the metal comes into contact with air, however, a chemical reaction begins on the surface. The shiny appearance of freshly cut alkali metals is due to metallic luster. Metallic luster is the ability of a metal to reflect most of the light falling on its surface. Metals possess a large number of free or delocalized electrons that can absorb incoming light energy and then re-emit it almost immediately. This reflection of light gives metals their characteristic bright, mirror-like appearance. Because alkali metals have mobile electrons within their metallic structure, freshly cut surfaces appear smooth, highly reflective, and silver in color. The image describes several features of a freshly cut alkali metal. It has a bright silver color, a metallic luster, a smooth reflective surface, and high light reflection. These characteristics are typical of clean metallic surfaces before any chemical reaction occurs. However, alkali metals are among the most reactive metals in the periodic table. Their general electronic configuration is Ns, meaning that every atom contains only one valence electron. This single outer electron is weakly held by the nucleus and can be lost very easily. As a result, alkali metals react rapidly with substances present in the surrounding environment, especially oxygen and water vapor contained in the air. The image illustrates oxygen molecules approaching the sodium surface and reacting with it. As soon as oxygen comes into contact with the freshly exposed metal, a chemical reaction begins. During this reaction, sodium atoms lose their outermost electron and combine with oxygen atoms to produce sodium oxide or related oxygen-containing compounds, depending on the environmental conditions. The overall reaction can be represented in a simplified form as 4Na plus O2. Now in practice, sodium may also form sodium peroxide under certain conditions, while potassium can produce potassium superoxide because of its greater reactivity. Regardless of the exact product formed, the important point is that an oxide layer develops on the metal surface. The image shows this process in the sequence. Freshly cut metal exposure to air reaction with oxygen oxide layer forms surface becomes dull. This sequence explains exactly why the shiny surface disappears. The oxide layer that forms on the metal is not smooth or highly reflective like the fresh metallic surface. Instead, it is rougher and scatters light in many directions rather than reflecting it uniformly. Consequently, the metal loses its bright metallic luster and appears dull gray. The image also emphasizes that alkali metals react not only with oxygen, but also with moisture present in the atmosphere. Even though the amount of water vapor in air is relatively small, it is sufficient to react with highly reactive alkali metals. When sodium reacts with moisture, it forms sodium hydroxide along with hydrogen gas. According to the reaction, 2Na plus 2HO, 2NaOH plus H. The sodium hydroxide formed on the surface further contributes to the dull appearance of the metal. Thus, exposure to ordinary air causes both oxidation and reaction with moisture, making the surface lose its shine very quickly. The image summarizes the changes occurring after exposure to air. It states that the metal reacts rapidly with oxygen, forms an oxide layer, loses its shine, and becomes dull gray. These changes occur because the clean metallic surface is gradually covered by chemically formed compounds that no longer reflect light effectively. The rapid loss of metallic luster is actually a consequence of the high chemical reactivity of alkali metals. Since they possess only one loosely held valence electron, they readily lose this electron to oxygen atoms. The greater the tendency to lose electrons, the faster the oxidation process occurs. Therefore, alkali metals become dull much more rapidly than less reactive metals. This behavior is very different from metals such as gold or platinum. Gold remains shiny for years because it is extremely unreactive and does not easily combine with oxygen or moisture. Iron reacts more slowly, producing rust over a longer period. Alkali metals, however, react almost immediately after exposure to air because of their exceptionally high reactivity. Since alkali metals react so rapidly with oxygen and moisture, they cannot be stored in open air. The image shows sodium being kept inside a container of kerosene or mineral oil. These liquids prevent oxygen and water vapor from reaching the metal surface. Because no contact occurs between the metal and the atmosphere, oxidation is prevented, and the shiny metallic appearance is preserved. This storage method is extremely important in laboratories. Sodium, potassium, rubidium, and cesium are normally stored under kerosene, liquid paraffin, or mineral oil. These liquids are chemically unreactive toward the metals and act as protective barriers against air and moisture. If alkali metals were stored in open containers, they would rapidly oxidize, lose their shine, and eventually undergo much more vigorous reactions. The image also compares two situations. In one container, sodium is stored under oil, preventing contact with oxygen and moisture. As a result, the metal remains bright and shiny. In the other container, sodium is exposed directly to air and moisture. It quickly reacts, forms an oxide layer, and becomes dull. This comparison clearly demonstrates the importance of proper storage. The silvery appearance is therefore considered a temporary property of alkali metals. It can only be observed immediately after the metal is freshly cut or when the metal is protected from the atmosphere. Once exposed to air, the appearance changes rapidly because chemical reactions begin almost immediately. This property is closely related to the ends electronic configuration of group 1 elements. The single valence electron is easily removed, making these metals highly reactive. Their tendency to lose electrons not only explains their chemical reactions, but also explains why their shiny surfaces disappear so quickly. As we move down group 1 from lithium to cesium, the outermost electron becomes even easier to remove because atomic size increases and ionization energy decreases. Consequently, the heavier alkali metals react even more rapidly with oxygen than lithium or sodium. Potassium loses its shine faster than sodium, while rubidium and cesium react so rapidly that they require even more careful handling. The shiny metallic surface also demonstrates an important principle about metals in general. A clean metallic surface reflects light because of its freely moving electrons. Whenever that surface becomes covered by oxides, hydroxides, or other corrosion products, light reflection decreases and the metal appears dull. Therefore, the appearance of the surface can often indicate whether a metal is chemically clean or has undergone oxidation. Freshly cut alkali metals possess a bright silvery appearance because their clean metallic surfaces strongly reflect light through their mobile electrons, producing a characteristic metallic luster. However, due to their high chemical reactivity and NS electronic configuration, they rapidly react with oxygen and moisture in the air. This reaction forms a thin oxide and hydroxide layer on the surface, causing the metal to lose its shine and become dull gray. To prevent this oxidation, alkali metals are stored under kerosene or mineral oil, which keeps oxygen and moisture away from the metal surface and preserves its bright silvery appearance. This behavior is one of the most distinctive physical characteristics of the alkali metals and provides an excellent example of how atomic structure directly influences the observable properties of an element. One of the most important physical properties of S-block metals is that they are excellent conductors of both electricity and heat. This property is shared by the alkali metals of Group 1 and the alkaline earth metals of Group 2, because both groups contain free-moving electrons, also known as delocalized electrons. These electrons are not permanently attached to any one atom. Instead, they can move freely throughout the entire metal. The presence of these mobile electrons allows electrical energy and thermal energy to travel easily through the metal, making S-block elements very good conductors. To understand why S-block metals are good conductors, we must first understand metallic bonding. In metals, the outermost valence electrons are not confined to individual atoms. Instead, the metal atoms lose control of their valence electrons, and these electrons become free to move throughout the crystal. As a result, the metal consists of a regular arrangement of positive metal ions surrounded by a large number of free, moving electrons. This model is known as the electron sea model, or the sea of delocalized electrons. The image illustrates this idea very clearly. At the bottom, many Na ions are arranged in a crystal lattice while numerous blue electrons move freely between them. These electrons are called delocalized electrons because they are shared by the entire metal rather than belonging to one particular atom. The attraction between the positive metal ions and these free electrons forms metallic bonding, which holds the metal together. The same free electrons that hold the metal together are also responsible for its ability to conduct electricity. Electricity is simply the flow of electric charge. Since electrons carry a negative electric charge, they can transport electricity if they are free to move. In S-block metals, these electrons are already mobile. When an electric potential or voltage is applied across the metal, the free electrons begin moving in one direction. Their movement creates an electric current. The image shows this process inside a sodium conductor connected to an electric circuit. The arrows indicate electrons flowing through the metal, while a light bulb connected to the circuit glows because electric current passes through it. This demonstrates that sodium allows electricity to flow easily from one end of the conductor to the other. The image also explains several important characteristics of electrical conduction. It states that S-block metals contain free-moving electrons. Electric current flows easily. They have low electrical resistance and are therefore used in electrical applications. Low electrical resistance means that electrons can travel through the metal with very little opposition. As a result, very little electrical energy is lost while current flows through the conductor. The reason S-block metals have low electrical resistance is that their delocalized electrons move freely throughout the crystal lattice. Since the electrons are not tightly bound to individual atoms, they respond immediately when an electric field is applied. This rapid movement of electrons allows electrical energy to travel quickly through the metal. The same free electrons are also responsible for the excellent thermal conductivity of S-block metals. Thermal conductivity refers to the ability of a material to transfer heat from one place to another. When one end of a metal is heated, the electrons in that region gain kinetic energy and begin moving more rapidly. These energetic electrons then collide with neighboring electrons and metal ions, transferring energy throughout the crystal. This process spreads heat rapidly from the hot end to the cooler end of the metal. The image demonstrates this process by showing one end of the sodium rod being heated with a flame. The arrows inside the rod indicate thermal energy moving toward the opposite end. A thermometer on the right shows that heat is successfully transferred through the metal. This illustrates that heat flows efficiently because the free electrons carry thermal energy from one region to another. The image further explains that heat transfers rapidly, free electrons carry thermal energy, heat conduction is efficient, and this is a characteristic property of metals. Unlike nonmetals, metals possess a large number of mobile electrons capable of transporting energy very quickly. The diagram in the center summarizes this relationship using a simple sequence. Metallic bonding, free-moving electrons conducts electricity, conducts heat. This sequence explains that both electrical conductivity and thermal conductivity arise from the same fundamental property, the presence of free electrons inside the metal. The image also compares a metal with plastic. In the metal, many free electrons are present, so electricity flows easily and the light bulb glows. In contrast, plastic contains no free-moving electrons. The electrons in plastic are tightly bound within covalent bonds and cannot move throughout the material. Therefore, plastic cannot conduct electricity and is called an electrical insulator. This comparison highlights one of the most important differences between metals and nonmetals. Metals contain mobile electrons that allow energy to move freely, while nonmetals generally lack these free electrons and therefore conduct electricity and heat very poorly. Although all S-block metals are good conductors, there are small differences between Group 1 and Group 2. Group 1 metals contribute 1 valence electron per atom to the electron C, while Group 2 metals contribute 2 valence electrons. Because Group 2 metals provide more free electrons, they generally possess stronger metallic bonding and are often better conductors than the alkali metals. Nevertheless, both groups remain excellent conductors because both contain large numbers of delocalized electrons. The conductivity of metals also depends on temperature. At ordinary temperatures, S-block metals conduct electricity very efficiently. As temperature increases, the metal ions vibrate more strongly within the crystal lattice. These vibrations cause more collisions between moving electrons and metal ions, increasing electrical resistance slightly. Even so, S-block metals continue to remain good conductors compared with most non-metallic materials. This property has many practical applications. Electrical conductors are needed wherever electric current must flow easily. Although copper and aluminum are used more commonly because they combine high conductivity with greater mechanical strength and lower reactivity, S-block metals demonstrate the same fundamental principle of electrical conduction. Their ability to conduct heat also makes metals useful wherever rapid heat transfer is required, such as in cooking utensils, heat exchangers, and industrial equipment. The excellent conductivity of S-block metals is also directly related to their metallic character. Metallic elements readily lose their valence electrons, forming positive ions surrounded by a sea of mobile electrons. These mobile electrons explain not only electrical conductivity, but also many other metallic properties such as metallic luster, thermal conductivity, malleability, and ductility. The image emphasizes that the free movement of delocalized electrons is the reason S-block metals are excellent conductors of both heat and electricity. This statement summarizes the entire concept in one sentence. Whether electrical energy or thermal energy is being transferred, the same mobile electrons are responsible for carrying that energy through the metal. S-block metals are excellent conductors of electricity and heat because they contain a sea of free-moving electrons formed through metallic bonding. When a voltage is applied, these electrons move through the metal and produce an electric current. When one part of the metal is heated, the same electrons rapidly transfer thermal energy throughout the crystal, making the metal an excellent heat conductor. Because electrons move freely with very little resistance, S-block metals possess high electrical conductivity, high thermal conductivity, and are among the best conducting materials in the periodic table. This ability to conduct both heat and electricity is one of the most important and characteristic properties of metallic substances and is a direct consequence of their unique electronic structure.